Okay, so there we are. Those are our three equations of motion. Now we look at some application examples. So before we get into application examples, we will little bit specifically look at the different cases. Okay, so of
Sir, could you please scroll up as I was noting it down, please?
okay, I'll go back to that. Okay, finish now.
Yes, sir.
Okay. So the first case is when U is along the positive direction and A is also along the positive direction. So an example of that would be, just suppose this is our axis of motion, okay, and a particle starts from this position with an initial velocity U, which is in this direction, and with a uniform acceleration A, which is also in this direction. Okay. So suppose, it started with a U which was 10 meters per second and an A which was 2 meters per second square. So what we'd observe is that after some time t, the particle would be at this kind of position x with a velocity v. So our v would just become like 10 plus 2t, and our displacement, which is the change in position, would just become 10t plus t square as a function of time. So here this v would be in meters per second and the displacement would be in meters. So just the important thing, how the graphs will look. Okay, our velocity versus time graph and the displacement versus time graph. How they will look. So just a minute, I will just. So our V versus T graph or S versus T graph. So a V versus T graph would be a straight line with a positive slope. So because A is positive, the slope would be positive. And a S versus T graph. Now notice that is this kind of a quadratic function. So it would be a parabola or parabolic function such that the slope is increasing. So it would have increasing slope. So in general, for example, if you have this function and you are plotting the graph, if you were taking unlimited domain, okay, then you would see that this graph it would have roots of 0 and -10. No? So it would be a graph like this, with this type of graph. But we take only positive time. So we would not take that negative part. So that's why this graph would be like this. So that's a S versus T graph. When the A is positive and U is also positive. Okay, so this is the first case. Okay. Now let's come to the second case, which is a more interesting one. If A is negative, so U is positive, but A is negative. So in that case, what will happen is that our V versus T graph will be a straight line with a negative slope. And accordingly, our S versus T graph will be a very interesting graph. It will be a parabolic graph that first rises and then decreases. So it has a negative slope. I mean, it has a decreasing slope. So I'm coming to that. So now in this relation, just imagine that A is a negative quantity. It's pretty obvious, but U is positive. So the y-intercept is positive, but the slope is negative. So it has a negative slope. But now imagine this graph. This graph is going to be very interesting. U is positive, but A is a negative quantity. So if A is negative, that means it's that type of parabola whose coefficient of the square term is negative. So it will be this sort of graph. So I'm not drawing it fully, it can continue but like this. Okay. So as you can see, the slope of the graph is initially it's positive, but it's decreasing. And then at some stage, the slope becomes 0. And then after that, the slope becomes negative. And it has an increasing value, but it's negative. So the slope is actually decreasing. Okay, so that is what so it reaches a maxima at a certain point. Okay. It reaches a positive maxima at a certain local maxima. You can see there's a point of local maxima over here. So again, if you understand this with an example, so the situation that we are looking at physically, how that will look like. So a particle sets off with a positive velocity, but it has a uniform negative acceleration. So as time is increasing, you can see that, for example, at t equal to 1 second, okay, its velocity would have reduced to 8 meters per second. At t equal to 2 seconds, its velocity would have reduced to 6 meters per second. And like that, at t equal to 5 seconds, its velocity would be 0 for an instant. And after that, it would start coming back because it has negative velocity. So for example, at v t equal to 6 seconds, its velocity would now become minus 2 meters per second, that kind of thing. Okay. So you can understand the pattern of the motion. Just follow how it's going. It's going like this and then turning back and coming back along the same straight line. So that's why our velocity versus time graph, I mean, if you just continue the graph even beyond this point, you can see it would start from 10, it would become 8 after 1 second, like this, like this. It would become 0 exactly at 5 seconds. At 6 seconds, it's becoming minus 2, and so on and so forth. So accordingly, our displacement, you can see it's going like this and then coming back like this. So it's at 5 seconds, it's reaching whatever maximum displacement it had. After that, it's turning back. It turns at t equal to 5 seconds. This particular case, okay, because our v is equal to 10 minus 2t and our s is equal to 10t minus t square. So you can see that this graph will have, yes, Janvi.
So we're saying it's actually tracing the graph again and again. It will go from s is equal to 0 to the point where it touches the x-axis again, then it will come back. So the same graph it's going to trace.
Yeah, it traces the same path. That's correct, Beta. It's like if you throw up an object vertically, it ascends and then descends. So while it is descending, it's like retracing the same path, but like a mirror image.
So if I go ahead of this beyond a certain time, it's gone from x is equal to 0 to some x is equal to x, and it's come back to x is equal to 0.
Yeah,
Then
and then it can even go. Yeah, in the opposite direction, and it can even go to negative x. If so, for example, if you're standing on a balcony on the 10th floor and you throw a ball vertically upwards, so it first goes up, then retraces its path, comes down. So then as it goes past you, is going past that x equal to 0 point, or y equal to 0, whatever axis you take. And then because there's space below, it's going further down. So that time its coordinate is becoming negative compared to its starting point.
So then what about the graph? So after that point,
the graph will also will show with it's going negative like that. S is what it,
yes, sir.
because S is always the position from where it started now. So imagine you are standing on the balcony and you've thrown the ball up and now it's gone past you and you're seeing it going down. So with respect to you, its displacement is negative now because you've taken the axis upwards as positive.
So sir, after this certain t, when it comes back, how will the graph look as it goes negative? It will.
This is the graph now with S versus T, the graph that we have drawn. See, as the ball is going up, your S is increasing. Then it momentarily it reaches the maximum and then it starts coming down. Na? So S is starting to decrease. Na?
Yes, sir. Sir, after it touches the x-axis again, at that point, sir, the velocity and acceleration are in the same direction. They're negative. So, sir, the graph after that, will it be part of a parabola or something like that?
This continuation is only the graph. See, this is only continuing. Your S like this,
Okay, sir,
and
I
your
got
V
it.
continues like this. So this is for indefinite amount of time. This can go until infinity, this graph. So there will just be a straight line with the negative slope going up to infinity. If the motion continues up to infinity, that is, and your S will also just keep going to more and more large negative values, till infinity. It's
Yes,
clear,
sir.
no?
Yes, sir.
Yeah. Okay, so before we continue, I'll just give you a quick refresher of parabolic graphs because they will come in a lot over here. Parabolic or quadratic graphs. Easy way to plot. Okay. So for example, if it is of the type just this, there's no constant term. Suppose if it is of this type and A and B are constants, then what you do is you factorize this. Okay. So once you factorize, you can see that the roots are x equal to 0 and x equal to minus b by a. That is, roots are the points where y is equal to 0. So once you got the roots, it's very easy to plot the graph because okay, this is one root 0 and let's say this is another root minus b by a, suppose, because one of these two is negative, suppose. Okay, so then the graph will be like this if a is positive, okay, and the graph will be like this if a is negative. Okay, and of course here I have assumed that minus b by 2a is the positive one. On the other hand, minus b by 2a could be a negative quantity also, in which case it would be like this. Our first root is 0, our second root is negative, and So this is how we plot a quadratic graph which has no constant term. It just has a coefficient of x square and a coefficient of x. And these are the most common type of parabolic graphs that you will encounter in kinematics. Okay, so you should really have no difficulty plotting these graphs. So I'll give you some numerical examples and we'll see some more properties also, like the position of the vertex and all this. Okay.
So why is minus b by a on the positive x-axis?
So I've assumed minus b by a is positive. No? That's why it should not be 2a, it should just be. A and b are just any constants. No? So they can be such that the value of minus b by a is positive. On the other hand, they can also be such that minus b by a is negative.
Okay.
Really depends on their values. No? So there are two cases possible.
Okay.
And within the two cases, there are two other cases possible. No? That it could be such that minus b by a is positive while a is positive or while a is negative. So accordingly, the parabola will be having, it will be opening upwards or it will be opening downwards. Okay. So the coefficient of x square is the first important thing, that if it is positive, it's a parabola opening upwards. A is positive, then the shape of the parabola is that it's opening upwards. And if A is negative, then the shape of the parabola is that it's opening downwards. That you can easily understand, because as A determines like what kind of value y will have when x is tending to plus or minus of infinity. If A is positive, y will be tending to plus infinity. If A is negative, y will be tending to minus infinity.
Yes.
So I know all of you can do the analysis using, derivative and maximum minimum and all that, but that is time taking, and this should become like second nature to us, quadratic graphs, because we analyze them a lot during kinematics. So just if you follow these simple guidelines I'm showing you over here, the moment you see a quadratic equation, you'll be able to visualize the graph. It will flash in your mind immediately. So for example, suppose I have y is equal to x square minus 2x. And all I have to do is I have to write this like this, that y is equal to factorize it. And you can see that the roots are 0 and 2. And the coefficient of x square is 1, which is positive. So it's a graph like this. So now you can visualize the graph very easily. So the moment you identified that thing, x square ka coefficient positive hai, and the roots are what, 0 and 2, immediately in your mind you have that clarity that okay, the graph is looking like this. It's passing through the origin point, it's passing through the point x equal to 2, and it's a parabola shaped like this. So obviously the shape of the curve is going to be something like this. For example, like we now have, so you can see two things here, that the roots are again 0 and 2. Okay. But this time A is minus 2, it's negative. It's a parabola shaped like this. Okay. So this graph will now look like this. Now I'll show you very quickly how to find the peak point and all that also. Okay. But first thing, let's just get used to the shapes. Okay. So just plot these two also.
So,
Yes.
so in the second graph, we should plot -2 on the graph, right?
Which one? The 4x minus 2x square.
Yes, sir.
नहीं बेटा देखो इसका रूट्स क्या है 0 and 2 है ना. Put y equal to 0
Oh, yes, sir. Yes.
है ना. So a by b is still a positive quantity ना, because a is -2 but b is 4.
Yes.
Oh, but I have just made a mistake here. No, it's fine. Okay, so got the other two graphs. So I'll just plot them one by one. You can verify your own graphs. Okay. So, this should become like second nature to you. It should not take too much time. You look at the function and you should immediately be able to visualize the graph in your mind. Okay. So you can see this has roots of 0 and -2 this time. And the coefficient of x square is positive. So it's a graph like this, but it has a negative root. Okay. So immediately you understand that it's a parabola, but it's like going to have its what we call its vertex on the negative side. Vertex is the point where it turns, or the critical point in the language of calculus. Okay, so one root is 0, but one root is -2 this time, and it's a parabola opening upwards. So that peak point, in this case the dip point, is somewhere. Okay. So for example, if this was a displacement versus time graph, then we would just ignore the negative side. We would just consider what's happening on the positive side of time. So it would be, on the positive side of x alone, this graph would be like this. So it would not be showing any maximum minima. It would just be showing always increasing. Similarly, the final example. To factorize this, you can take -x common and you have 2 plus x. So this time you can see it has one root 0 and the other root -2 again, but the coefficient of x square is negative. So it's like this. So instead of a dip point, it's going to have a peak point, but that peak point is going to be on the negative side. Roughly speaking, something like this. So anytime you have a quadratic function you are plotting, which does not have a constant term, it only has coefficient of x and coefficient of x square, It's very, very easy to visualize. Okay. And I'll show you next that even if you have a constant term, you can still use this plot, this trick to plot the graph. You just have to transform it. I'll explain what we mean by that. But in the current application we are doing that S is equal to ut plus half at square. The formula only is such that there is no constant term. There is a coefficient of t and there's a coefficient of t square. So actually this is precisely what we'll be using. And in that also in the graph, we'll be looking only at the non-negative side of the domain of t. There's no negative t. Okay. Now the next thing, the next thing to keep in mind is that for this thing, the vertex of the parabola will be at the midpoint of the roots. Okay. So I'll just show two of the cases here, but you can generalize it to all four cases that we've seen above. That is all four types of combinations of A and B. Positive, 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 negative, negative, positive, negative, negative. All cases it will work. Okay. So I'm just showing these two cases here. So this is a case where A is positive and B is negative. There is a case where A is negative and B is positive. So the roots so we'll now use a generic term for the roots. So we'll call this root as alpha and this root as beta. So you can see in this case, this is our alpha and this is our beta. Okay. So now what this is saying that the vertex, now vertex is which point? The vertex is the turning point or the critical point. So in coordinate geometry language, it is called vertex. In calculus language, it is called turning point or critical point. Okay. So this vertex will occur at the midpoint of the roots. That is the symmetry of the parabolic graph. You can also show this by differentiation because the vertex is the point where your derivative is zero. So that is the calculus proof of this, that always the vertex occurs at a symmetry point because the parabola is divided into like a mirror image of itself by this line. So that happens because at the vertex, which is basically the turning point, the slope should be zero. So you can see 2ax plus b should be zero. So x should be minus b by 2a which is basically equal to alpha plus beta by 2. It's the midpoint of the roots. Okay. So in this case, the minima of the function will occur here. You can call it global minima, you can call it local minima, it's one and the same thing. In this case, the maxima of the function will occur here. So this is going to be another important thing for us. Yes, Rijita, beta, you have a question?
Yes, sir. Sir, how did you understand plus or minus b?
From the way I'm drawing the graph now. You understanding? Now? You mean A and B plus or minus how I've taken?
No, sir, just b.
Just B now? Okay, so see what I'm doing is AX square plus BX. Now when it will look like a parabola opening upwards, that is the first case, when A is positive,
Yes,
and when
sir.
it will look like a parabola opening downwards, when A is negative. So that's how I
Yes, sir.
understood that here A is positive, here A is negative. Now the second thing is, in both the graphs, I've taken my second root on the positive X side, not on the negative X side.
Yes, sir.
So my B by A should be what kind of quantity? It should be negative because minus B by A should be positive.
Yes, sir.
So understood now how I've taken that?
Sir, in the second case, why is it positive?
Because see, A is negative already. The parabola is opening downwards.
Yes, sir. I got it.
So B must be understood now.
Yes, sir.
Okay. So without using calculus, in this type of thing, we can find the coordinates of the vertex. Because, okay, so I'll just, so you note this down and then quickly practice this couple of questions. So you might think that I'm digressing from kinematics here, but actually you will see that by using this trick, when we come to the kinematics problems, you will be very fast at visualizing the problem and doing the calculation. Okay. Right up to projectile motion, actually, not only in 1D kinematics, but right up to projectile motion, this kind of graph visualization is going to help you a lot. Okay. So for example, I have y is equal to, let's say, 4x minus x square. Okay. Plot the graph and find the coordinates of the vertex. Okay, people, anybody else got the answers? Aditya, very
Yes,
good.
sir.
That's correct. Yeah. Send me the answers, please, on text if you got them. So what was the first one? 4x minus x square. So you can see you don't need to do dy by dx and all that for this particular type of function because you have learned this very specific method of working it out. Just factorize it. So you can see that the roots are 0 and 4, and the coefficient of x square is negative. So it's a parabola like this. So this will be the type where the vertex is a maxima point. So here the vertex will have an x coordinate which is midpoint of 0 and 4. So this is my vertex point's x coordinate. It will be 2. And the y coordinate we'll have to find by just substituting 2 over here. So vertex that x equal to alpha plus beta by 2. So that's 2. So y will become 4 into 2 minus 2 square. So that's 4. You can see that the so this is the thing I want you to be able to do very fast. Okay? The moment you see a function of this type, you should be able to visualize the roots, the shape of the parabola, whether it's opening upwards or downwards, and therefore calculate the position of the vertex. You will see that it will help you immensely in solving those type of questions very fast. The JEE mains level type of questions. What was the second one? 3x square plus 8x. This is the vertex. So this kind of analysis, it should be easy to do now.
Sir, it was 9x, right? Not 4x.
Mm-hmm.
Sir, in the second part, sir, x square minus 9x, right?
3x square minus 9x.
Oh, yes, sir.
This, huh?
Yes, sir.
This only you're saying, it's 9 only. That's why. Right, so all of you got the graphs, understood the trick method now.
Yes.
Yes, sir.
Okay, so this trick is very specific for this type of parabola. Y is equal to ax square plus bx. There's no constant term. Okay. Now, very quickly, I'll show you that even if there is a constant term, how we can make use of this same trick. Okay. Even though actually immediately in kinematics, we won't even need that. But in general, for the general equation that is quadratic function, y is equal to ax square plus bx plus c, we can use transformation. Method. Okay, so what is the transformation method? I'll show you. Okay, in maths, you will learn a lot of tricks of transformation later, but I'm just showing you a general one. If you have any given functions graph, okay, suppose this is the graph of y is equal to fx. Okay, and now you want to plot the graph of a new function, which is y is equal to fx plus some constant. C is a constant. Then all you have to do is you have to lift this whole graph up by c. So just lift it everywhere by c. Okay. So very simple example. Suppose we have y is equal to x. Okay. Any graph will work. Okay, so this is y equal to x. Now what will the graph of y equal to x plus 1 look like? Just lift this whole graph up by 1. So any point you can see here. Suppose this was the point x equal to 1. Here y was equal to 1. But here y will become 2. I mean, let's say this was half. This is half. So here y will become 3 at this point. So this whole graph is lifted up by 1 unit. Okay. So you have, let's say, graph of y is equal to sine x. You know, like this looks like this. Now I have graph of y is equal to sine x plus 0.5, let's say. So that will look like this. Similarly, if you have the graph of, that will look like this one. So if c is negative, it will look like this. So this is the general transformation. So for example, now if you have, suppose I have this graph. Okay. So what I will do is I'll start with the graph of y is equal to x square minus 2x. So that I know looks like this. Let's do a quick mental calculation so you can see it looks like this. So now I want to transform this to this graph. So I have to just lift this whole graph up by 3 units. So when I lift this up by 3 units, you can see this vertex point will go up here. We'll go to 1, 2. Okay, so this graph will not look like this. You can see it does not have roots. Yes, okay. So a lot of people have unit tests in school, I think.
Site
Sir,
is
it's
cancelled.
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 Oh, it's cancelled. Is it confirmed?
Yes,
Yes,
sir.
sir.
Actually, it is postponed.
Okay. Jairaj, Dhruv, for you also?
Yes, sir.
Okay, okay. So then
So
we
let
just
me check.
continue for 2 minutes more. Very good. Couldn't have been cancelled because of the rain, could it? Because it's an online test, but anyway.
Yes, sir. Rains only, sir. Wi-Fi network is down in many areas.
Oh, okay. Yes. Okay, fine. Understood. Okay, so hope you have understood this transformation method. So you don't have to do any other analysis. For example, here maxima, minimum, all this is not required because it's a quadratic function. So given any quadratic function, the general method is what we do is given anything like this, ax square plus bx plus c. So first remove the c from the analysis. So plot ax square plus bx. Okay, understand what the roots are. From that, understand what the vertex is, and then transform. So when you transform, it will go upwards for c being positive. It will go downwards for c being negative. So any graph like this you can plot now. Any quadratic graph that is. So for example, plot and find the vertex for just try both of these out and then think enough. Okay, let's do one with negative also. Okay, very good. So I'll just quickly verify the graph. So I'll take you through the same process in each one of them. So x square plus x plus 1. So if we start with the simpler graph of x square plus x, we can see that it has roots 0 and -1. And this one has vertex at -12. The y coordinate becomes -1/4. You can just put it here and you can see. So now this graph, you just have to lift this whole thing up by 1 unit upwards. So the coordinate of the vertex will become -1/4 plus 1. So it will become +3/4. So you can see that it will no longer have real roots. It will be such a graph whose global minima only is a positive quantity. So it never cuts the x-axis. So I have to lift this whole thing up by +1. So this point will go up here. In this graph. Oh, sorry. This is -12. The y coordinate is 3/4. You can see that's our vertex. So this is a very effective way of dealing with parabolic graphs. Okay, so start with the transformed one. And then transform this up by 2 units. So you can see no lengthy calculations, no discriminant, derivative, critical point, nothing like that is required. It's very simple and very effective way of plotting graphs for quadratic functions. Okay, so now you can use this method very effectively. Okay. So you can review this from the notes later in case you haven't noted down. Okay. So you can use this very effectively for displacement time graphs. So S versus T graph for uniformly accelerated 1D motion. So let's take U as, let's say, plus 4 meters per second square and acceleration as plus 1 meters per second square. Let's take U as plus 10 meters per second square and acceleration as minus 4 meters per second square. Sorry, meters per second. So in this case, S is equal to ut plus half at square. So you can take this kind of thing. Okay. So the graph in general would have looked like this, but obviously we'll consider only the positive side. So this one now you can see it will be a graph of this type now, with one root 0 and one root 5 and the peak at 2.5. So we will not consider the negative side of the graph. We will only consider. So you can see that. So what happens here, you can immediately analyze that the motion is in positive direction from 0 to 2.5 seconds. Okay. Then turns back at t equal to 2.5. Okay. And goes past the initial position. So all these things you can analyze in a flash. See, at t equal to 5 seconds. So it has a negative displacement after t equal to 5 seconds. Okay. And the maximum displacement is reached at maximum positive displacement. So that's equal to the value of S at t equal to 5. Sorry, 2.5. So you can see that that is 5 into 2.5. So 12.5 meters. You can see that this maximum displacement is. Now, of course, if it keeps going on the negative side indefinitely, then the magnitude of displacement will become infinity after some time, or very large at least. Okay. But thinking of displacement as an algebraic quantity, we will still say that the maximum of displacement is plus 12.5 because that's negative. It's not positive. So you can see how much graphs are going to help us in analysis of these type of problems. Okay. Yes, so I'm going to talk to you about the homework. Okay. So today actually we got into this fully, so I did not get the time to ask you if you have any doubts pending from calculus, especially exercise 4, which is application of calculus in kinematics. So we will pick that up in the next lecture, but in the meantime, in the week also, you can send me any doubts via WhatsApp if you have. So priority, you have to finish, if anything is pending, exercise 4 of calculus module, that is applications of calculus in kinematics. Or rather applications of calculus in kinematics. Anyway, so that is one thing. Okay. Now, apart from that, I will also send you a worksheet for this week. But apart from that, now, this is the point when I will also talk about reference books. In addition to module, so the first reference book you can think about is Concepts of Physics. Okay. It comes in 2 parts. That is for your 11th. And part 2 for your 12th. Get hold of both the parts together. Okay. You will need them anyway. So Concepts of Physics by Dr. H.C. Verma. This is so this we will be using for problem solving. Solved examples. Okay. Objective questions and subjective questions. And the most important are going to be the subjective numerical problems. They're not subjective theory problems. This is going to be the most important aspect of this book. Okay, this is not for theory. Okay, this book is not for reading theory. In the second book will be fundamentals of physics. So from kinematics chapter onwards, you can start referring to these reference books. You can also go through the chapters like units and dimensions and little bit about calculus before the kinematics chapter, but you won't need it. Actually, it won't be necessary. You start with kinematics. Okay. So this is also in 2 parts by authors Robert Resnick, David Halliday, and Cream. So this is get the student edition because the hardbound American edition is way too expensive. You don't need that. Okay. So this is specifically for theory reading and reference. Not for solving problems. Okay. Now you can also alternatively use NCERT. For theory reading. but I would recommend using this book. And for additional problem solving, especially when you're doing revision of a chapter, you can use this book. So this is actually a series of many books. There is Mechanics 1 and 2 in 2 parts. Okay. Then there is Waves and Optics. Sorry, Waves and Thermodynamics. And there is Modern Physics and Optics. And okay. So it's a 5-part series actually. So for the moment, you can just get hold of Mechanics 1 and 2, which will be running at least for the next 4 to 5 months before we come to any other part. But you can also get hold of all 5 parts. So this third book is what I'm recommending for you people for your additional numerical problem solving, especially for the JEE Advanced pattern. So this should be more than enough. For the more ambitious people here, you also have, like, optionally can do selected problems from Problems in General Physics by Erodo. This will also orient you towards physics Olympiad type problems. And then there are few other sources that you can maybe later think about if you feel comfortable with all of this. Okay. Remember that your first priority is to complete problems from the module, okay, and the worksheets and exercises that we do. If you complete that, then as far as your exam preparedness is concerned, like more than 90% is done, even at JEE Advanced level. But for additional practice, you can use these sources, and for additional theory reading, you can use this. Okay. So that's the thing for today's session. Sorry for exceeding the time, but needed to discuss about these reference books also, apart from other things. So that's it for today's session, people. Wish you all the best. Thanks for attending.
Thank you, sir.
Have a nice day.
Thank you, sir. Bye, sir.
Sir, bye, sir.
Bye, sir.
Bye, people. Bye.
Thank you, sir. Bye, sir.
Bye, people. Bye.